numbers. Now, most of the books containing these square numbers, they do not show these patterns. At one place you will not find all the patterns, but by following this series of videos you will be able to understand these square numbers in a better way and obviously appreciate the kind of patterns we observe in numbers when we study mathematics. So here I go. This is the first part of the video and I'll tell you three interesting patterns observed in square numbers. Now this is the first one. See, whenever we write any square number, that square number is either a multiple of 4 or when you divide it by 4, only 1 is the remainder. So let us take one example. Obviously this is except 1. We cannot have any pattern for 1. So except 1, all square numbers are either divisible by 4 or leave remain, or you can write it in a simple language also. We will not use the word remainder, or 1 more than exact multiple of 4. Now let us try and understand this using some examples. Suppose we have 3 square. Now see, 3 square is 9. You can write 9 as 8 plus 1. So 8 is perfectly divisible by 4 and we have 1 more than the exact multiple of 4. Now let us take some more examples. Say we have 6 square. Now 6 square is 36. 36 is 4 into 9, which is exact multiple of 4. Take more numbers. Say we have 11 square, which is 121. This is 120 plus 1. See, we have an exact multiple of 4 and 1 added to that number. Say we have 15 square. 15 square is 225. It is 224 plus 1. Now 224 is divisible by 4 and again 1 is the remainder. Take two more examples. Say we have the square of 24. 24 square is 576. It is an exact multiple of 4. The remainder is 144. So 576 is exactly divisible by 4. Likewise, if you take 30 square, it is 900. 900, 4 into 225. It is exactly divisible by 4. So see, if moreover, whenever you see even number squares, they are exactly divisible by 4, and whenever you see odd number squares, we have an exact multiple plus 1. So this is very important property of squares, and I hope you appreciate the kind of patterns we observe in square numbers. Now take one more pattern. In the second pattern, now you see, whenever we have a square number, suppose we have p square, the double of that number, if this is a square, perfect square, then the double of that number will never be a perfect square. Never a perfect square. Say, this is the example. Say we have 6 square. Now 6 square is 36. What is double of 36? It is 72. It is not a square number. Say 2 square is 4. 4 is a square. So if you take double of 4, you get 8. It is not a square. So double of square numbers are never square numbers. So take more examples. Say we have 9. 9 square is 81. 81 is a square. So double of 81, 162 is not a perfect square. So all the numbers whose square we have taken, the double of that number, double of that square number will never be a perfect square. There is no pair of numbers which obey this equation. This equation can never be proved correct for any numbers. Yet another amazing pattern. And for the final pattern in the part 1, if you take the square numbers, see I take 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, 7 square is 49, and so on. You can write on and on. Now what is the pattern observed in these square numbers? See 1, if you see 4, it is 1 plus 3. See, I am adding odd numbers. 1 plus 3 is 4, 1 plus 3 plus 5 is 9, 1 plus 3 plus 5 plus 7 is 16, 1 plus 3 plus 5 plus 7 plus 9 is 25, 1 plus 3 plus 5 plus 7 plus 9 plus 11 is 36. Similarly, 1 plus 3 plus 5 plus 7 plus 9 plus 11 and 13 is 49. So this is one of the properties, very interesting properties of square numbers. What is this number whose square is taken? 2. So take first two odd numbers and add them, you get the square of that number. What is the number taken here? 5. So take first 5 odd numbers and add them, you get the square of 5. What is the number taken here? 7. So take first 7 odd numbers, add them, you get the square of 7. This pattern is true for infinite number of squares. So the first amazing pattern which I am going to tell you about square numbers is when we take the square of any number and square of its consecutive number. Say I have denoted it by n square and n plus 1 square. Now how many numbers will be contained between these two perfect squares, consecutive perfect squares? This you can find by using the formula 2n. 2n non-perfect squares, non-perfect square numbers. Now to understand this, let us take an example. Suppose we have n equal to 3. Now see, if you put n equal to 3 here, this number becomes 3 square, which is 9, and this number 3 plus 1 4, 4 square, it is 16. So between 9 and 16 you find 10, 11, 12, 13, 14 and 15. So how many numbers are there? 6 numbers. And how we have obtained these 6 numbers? This is n was 3. So 2n is 2 into 3, that is 6 numbers are between two consecutive perfect square numbers. Now let us take one more example to understand this in a better way. Say I'll take a larger number now. Suppose we have n equal to 11. Now when we have n equal to 11, that implies this number 11 square 121 and 11 plus 1 12, 12 square 144. Now I want to find how many numbers are contained between 121 and 144. Just write twice of n equal to 11, 11. It is 22 numbers which are between two perfect squares 121 and 144. Finds wide applicability when you can put the values of n as large numbers where the squares of the numbers are in thousands. You can always calculate how many non-perfect square numbers lie between two consecutive perfect square numbers. So this is the first pattern. Now the second pattern. Now what we do is we take any two odd numbers, any two consecutive odd numbers, and we multiply them and then we add 1. Multiply two consecutive odd numbers and add 1. Now see what happens when we do this. Suppose we have 7 and 9. These are two consecutive odd numbers and add 1. 7 into 9 is 63. And add 1 to this, you get 64. Now what is 64? 64 is a perfect square and this is 8 square. So where does 8 lie? It lies exactly between the two numbers whose product we have taken initially. So let us verify whether this pattern is true for some other numbers as well. Now see, I am taking two more consecutive odd numbers, say 11 into 13 and then adding 1. 13 into 11 is 143 and add 1 you get 144. 144 is 12 square, so 12 lies in between these two numbers 11 and 13. Amazing, isn't it? Let us take one more. Say we have 31 into 33 plus 1. So 33 into 30, 33 into 1, 33. So 3 carry, 99 and 3, 102. Plus 1, you get 1024. And what is 1024? It is 32 square, which lies between 31 and 33. Now this pattern, I have done it for odd numbers. Now let us check it for even numbers. For even numbers, you take say 8 and 10, then add 1, you get 80 plus 1, 81. 81 is 9 square, so you get the number between 8 and 10, it is 9. Take some larger numbers, say 20 and 22. 20 and 22 are two consecutive even numbers. We add 1 to this. So this is 440 plus 1, it is 441. And what is 441? It is 21 square, which lies between 20 and 22. So this pattern is true both for odd numbers and for even numbers alike. We'll take one more example and then we'll conclude this. Say we have 28 and 30, then we add 1 to this. This is 840 plus 1, it is 841, which is 29 square, and 29 lies between 28 and 30. So yet another amazing pattern in square numbers. Now the first amazing pattern is observed when you square any odd natural number. Now suppose I am taking the example of 7. Now the 7th square, as you all know, is 49. So the square of any odd natural number, it can be expressed as the sum of two consecutive natural numbers. So whenever you take the square of any odd number like 49 here, you can express it as a sum of two consecutive natural numbers. Now see, 49 is 24 plus 25. These are two natural numbers which are occurring in succession. So these kind of patterns are very useful in developing mathematical aptitude among small children. If you tell these to small children, being parents, being a teacher, any mentor or elder brothers, sisters, you have to tell these patterns to small children so that they develop the ability to accept mathematics as a interesting subject. So we can take some more examples like this. Say suppose you have 9 square. Now 9 square is 81. Now 81 can be expressed as 40 plus 41. See, again the consecutive natural numbers. Likewise, some more. Say we have 15 square. It is 225. So now 225 can be expressed as 112 plus 113. Likewise, you can go on and take more examples of the squares of odd natural numbers. Every time you will find this amazing and useful pattern. Now the second pattern is more amazing. You will be surprised by this one. Now see, suppose you have the squares of numbers which contain only ones, like 11. 11 contains only ones, so 11 square is 121. Now what I am going to do is, I am going to multiply this number 11 square by the sum of digits in 11 square. sum of digits in 121, that is the square of 121. So if you do this, you get 121 into sum of digits in 121, so 1 plus 2 plus 1. Now this will come out to be 121 into 4, that is 484. Now the number which we have obtained is somehow related to the initial square which we have taken. How many ones were there in 11? 2 ones. So now this number will be the square of 22. Likewise, if you take 3 ones, suppose you take the example of 111. Now the 111 square, if you are aware of another pattern in the square of the numbers containing only ones, you will know that the square of 111 is 12321. So when you multiply this by sum of digits in 1, 2, 3, 2, 1, you get 1, 2, 3, 2, 1 multiplied by 1 plus 2, 3, 3 plus 3, 6 plus 3, 9. And this number is 9, 9 2s are 18, 9 3s are 27, plus 128, 8 2, 9 2s are 18 into 20, 0 2, and 1s are 9 plus 2, 11. So this is 1108889. Now, how many ones were here? There were 3 ones. So this number will be the square of 333. 2 ones, 2 2. 3 ones, 333. And if you want to check one more, we can do that. Take 1111 square multiplied by sum of digits in, now what is 1111 square? 4. So 1 2 3 4 3 2 1. So this number 1 2 3 4 3 2 1 when multiplied by, this is 10 16, gives you another number. That number I have already calculated for you. That number is 19749136. And this number happens to be the square of which number? Yes, you guessed that right. There are 4 ones, so 4 4 4 4 square. Isn't that amazing? So many patterns in square numbers, and if we appreciate the beauty of mathematics, obviously mathematics learning becomes very easy and joyful experience. So keep sharing and subscribe the channel if you like it.